Let's talk about what we refer to as even odd functions, or even odd properties. I'm going to call them functions because it's just eventually we're going to talk about the sine and cosine graphs and their functions when we look at them as graphs. If you guys remember back to college algebra, okay, algebra 2, you probably even talked about it a little bit. An even function is a function in which it is symmetric about your which axis? The y-axis. Okay, even is an even function is a function symmetric with the y-axis. An odd function is symmetric about the origin. Okay, meaning that we can fold it on the y-axis and then the x-axis, and essentially the two parts of a graph would lay on top of one another. Okay, and we're going to see a little bit of that here, hopefully maybe by the end of the period. Now, whether you need to know that and kind of keep track of which ones are even functions, which ones are odd, I don't really care. I want you to know the properties. I want you to be able to apply these because it's going to be a tool that becomes pretty useful for us. It says sine, cosecant, tangent, and cotangent. Those are the ones that are odd functions. Okay? And we'll come back once we graph these things. And it's not as easy to see on the unit circle that they're odd functions. But it's a lot easier once we graph them as waves. It's a lot easier to see they are odd functions. The cosine and the secant then are your even functions. So those two, you fold on the y-axis, they would overlap each other. The cosine folds onto itself, and the secant folds onto itself. But when we see those phrases even odd, they're talking about essentially the symmetry, okay, of those functions. Now, using the unit circle, the purpose of knowing these properties is so that we can avoid using negative angle measurements. So we can replace and use the unit circle in a much more kind of friendly format, okay, with a lot less, I think, confusion. But because if you look at these, all of them start with a negative t value, right? A negative input, which would mean that, and again, if we're making the argument that theta and t are the same in the unit circle. So if we think about it as, negative, because sometimes you do see textbooks do this, negative, or sine of negative theta is equal to negative sine of theta, because right now RT and theta are the same thing, right? Okay. Or the same quantity, so they're the same input. These even odd properties allow us, and all of them, to transform the function so that we're dealing with just a positive version of the angle, right? Okay. Most of us probably feel real comfortable moving, counterclockwise around the unit circle, and maybe knowing the points that are on the unit circle. It's a real big pain in the butt to do it counterclockwise and know all the points that exist on that. For instance, okay, show you the purpose of why we want to learn these and why we want to try to commit this stuff to memory as soon as possible. If I have these two circles, so what I'm going to do is I'm going to write the unit circle out, moving that direction, just for a few values. So obviously there'd be 0, that'd be pi over 2, that'd be pi, 3 pi over 2, right? Let's go, I'll put the pi over 4s in as well. And I'll show you guys how I know these here in a little bit. If you can count, you should be good to do that, okay? That's using t equaling a positive number, okay? Well, if t was a negative number, if t was going this way, t is a negative number, how far would that be? Is that the same as that distance there? Yeah, but it's in the opposite direction, right? So when I label this as negative pi over 2, this would be negative pi, negative 3 pi over 2, and now negative 2 pi. Does that kind of make sense to everybody? Then this point here would be negative pi over 4, negative 3 pi over 4, negative 5 pi over 4, negative 7 pi over 4. And my argument to you is that location there and that location there are completely different, right? Okay? Because if I'm traveling in a positive direction, let's see here where my markers go. If I'm traveling in a positive direction, that distance there, even though I get to that point going positive, and I can get to that point going negative, would you guys agree that this negative direction to get to that point is longer than this positive direction? Okay, so these two unit circles, we don't want to have to know this unit circle. Okay, once you know the other one and you're able to produce this one, this isn't all that bad. Okay, if you think about it, isn't this just kind of the if I take this one here and flip everything on the x-axis, it gives me this one, and then I negate everything. Does that kind of make sense? Okay. But we don't want to have to do that. That's a pain in the butt. Okay. So what do we do? Well, we're going to not do that or that. There we go. We're going to use these even odd properties that say if I want the sine of a negative t, that is equivalent to the opposite of sine of t. Let's do an example. If I say I want the sine of negative pi over 3, sine of negative pi over 3, what we're saying then is that equates to the exact same thing as the opposite of sine. Now it's the positive version of t, so it would be pi over 3. Okay, let's see how that works or why that works. If I had sine of negative pi over 3, negative pi over 3 is going to be right there. Okay, and the ordered pair that goes with that would be an x direction of 1/2 and a y direction of negative root 3 over 2. Okay, we'll talk about that in a moment, how I know that, all that kind of stuff. Okay, but if I did positive pi over 3, if I did this, wouldn't that point show up right there? Because positive pi over 3 is going to be essentially the reflection of that point, right? Those 2 points are reflections across the x-axis of one another. Okay, the ordered pair here is still 1/2. But the the y value is root 3 over 2, correct? So we're going to the sine of negative pi over 3. We're looking down here, it's that one right there, right? Negative root 3 over 2. Well, how can I make that equivalent to the sine of pi over 3? A sine of pi over 3 is root 3 over 2, right? They're not equivalent yet, right? How do I equate them? I need that negative, right? Okay. So that's kind of showing you that they are the same. The sine of the opposite pi over 3 is the same as the opposite sine of pi over 3. But why have that property? Why use that? It's because now I don't need to travel in this direction if I don't want to. Okay? I can say, well, I know they're asking for sine, let's say sine of negative 3 pi over 4. Sine of negative 3 pi over 4. So what that would mean to us, guys, is that I have to travel from there. Let me do this in purple. I would travel from there to about right here. And now I got to figure out what is that ordered pair. Okay? Well, it's going to be a lot easier to say, nope, I'm going to do it this way. The opposite of sine of 3 pi over 4. Because now I can travel to there, hopefully knowing what that ordered pair is. Anybody know what the ordered pair for 3 pi over 4 is? Root 2 over 2, root 2 over 2. The x is got to be negative though, right? Okay. Now, Sine of negative 3 pi over 4 is equal to the opposite of the sine of 3 pi over 4. What is the sine of 3 pi over 4? Root 2 over 2. We then need the opposite of that, right? And that allows us to quickly kind of determine, if I typed in sine, get the right mode here, I'm in radians. So I go sine of negative 3 pi over 4, hit enter, gives me negative root 2 over 2, right? Okay. It alleviates having to use negative angles, okay, if we can remember that property. Now we can do the same thing with cosine. Okay, cosine of t. Now let's do negative t. Let's think about this. Cosine negative, and let's just see if we can maybe help us write this rule. Okay, if I just say cosine negative t, so let's just go. Maybe that point right there, let's say that would t be negative pi over 6. So that would be t equals pi over 6, right? How does the x coordinate, because that's the cosine that we're interested in, relate for that red compared to the blue? Those x values should be what to one another? The same. So this x value actually ends up being root 3 over 2, and this one is root 3 over 2 as well. But they're the same, right? So the cosine of a negative angle is the same as the cosine of the positive angle, right? So why not just find the cosine of the positive angle? Does that make sense to everybody? So if they ask you what is the cosine of, negative, let's say, 5 pi over 6, negative 5 pi over 6, well, that would be this point here, right? Going that direction, 5 pi over 6 units, okay? Well, it might be a little bit easier for us to move in that direction of 5 pi over 6. That's t equals 5 pi over 6. That might be easier because now I might know, that's root 3 over 2, 1/2. The root 3 over 2 is negative. So the cosine of that point right there is identical to the cosine of that point, right? So I can say it's equal to cosine of 5 pi over 6 instead, which we then know is negative root 3 over 2. Does that make sense to everybody? That's not the only way we could do this. Think about this. Think about going, we know that we don't like negative angles a lot. I think this is probably quicker than this, but could I do this? Could I say cosine of negative 5 pi over 6 is equal to cosine of negative 5 pi over 6 plus 12 pi over 6? What did I just add to that? 2 pi. So if I stop here at that point, if I go this direction, stop at that point, isn't it the same thing if I would have started going around one more entire time, get back to the same point? So let's add 2 pi to that, and I get cosine of 7 pi over 6, right? Is this the point associated with 7 pi over 6? Yeah. Okay. That little arc right there would be pi over 6 beyond pi, so it would be 7 pi over 6. So you could do it that way if you want to. Okay. These are just techniques, guys, that allow us to get rid of dealing with negative angles. Okay, which I know, and in the past years, and even that I've been teaching, obviously the past centuries, why do people write this down? It's a fact, so that's one reason why we talk about it and discuss it. But it makes things easier. It creates efficiency for us in regards to gaining these values. Okay. What I always remember is that the sine of negative t, this one you have to negate it. You have to bring that negative out, and then that's going to give you that, right? the cosine of negative t, you do not need to negate. Okay? And because of that relationship, okay, what would you call tangent? Well, let me kind of answer the question. Let's write it this way, because I think, you know, there were 6 things there for you to remember, right? 6 properties. That's a pain in the butt. You already know that this thing here how could you, so you know, if I write these two as a fraction, right? You know that this one here is negative, the numerator is actually the negative sign of positive t, and the denominator is cosine of positive t, right? What would this thing here be called? What's sine of negative t divided by cosine of negative t? Tangent of negative t. And this would give you then, what's sine divided by cosine? Tangent. It's a positive argument now, but this was a negative and this was a positive, right? So there's where that negative comes back. Okay? And there's then the property for tangents. Okay, so however you want to decide these and try to commit them to memory, don't try to memorize them word for word, letter for letter, sign for sign. Try to develop kind of a phrase that might help you. I would think that, you know, I don't have a phrase in my mind, but I just know that the cosine one, I don't want to change anything. Cosine of negative angle, same as cosine of positive angle, right? And that means the sine is the one that I have to change. The sine is the one that has to be negated. And if I can get those two, I can get that one. I can get that blue one. Okay? And now that I got all 3 of those, can I use the reciprocals? All right, the reciprocals, whenever I have a reciprocal of a number, the sign has to be the same, right? Okay, so the cosecant is going to have that negation, just like the sine did. The secant is not going to have a negation, and the tangent will. Sorry, the cotangent will. Does that kind of make sense? Okay. We're going to mess around with that periodically throughout the rest of the course. You're going to see at some stage they're going to give us a negative angle, and I'm going to go right away, say, nope, not going to deal with it. I'm going to change it to this, okay, or change it to this. It just makes things a lot more convenient for us, okay. We always like that argument to be positive if it's possible, and it should be. Okay, so we did a couple examples of that. Let's do, you know, cosine of negative pi over 4. And this is the benefit, guys, of knowing our unit circle, which I'll show you here in a moment how to generate it on your own. But cosine of negative pi over 4 should be identical using the even-odd properties, should be equivalent to the cosine of pi over 4, right? Cosine is the x value. What is the x value of pi over 4? Anybody know? Root 2 over 2. Okay. And you can type this into your calculator, and that's what's going to get spit back to you. Okay. I'm going to put these up there. I think you probably already have them in your notes, but I do think it's probably beneficial to have them again. All right, so with those, remember, obviously your reciprocal identities, I'm not going to talk too much about those. Same concept that we talked about in chapter 5. If I know, obviously, and right now I guess they're presented to using, you know, cosecant t equals 1 over sine of t, but we could also say, can we say that sine of t is equal to 1 over cosecant t? Does that make sense to everybody? Okay. Kind of view it as, I say 2 is the reciprocal of 1/2. We can flip things around and say 1/2 is the reciprocal of 2, right? Okay. So you might, at some point, find it useful, I'm looking at that one, to say, and it's basically just doing a little bit of algebra here, guys. Cosecant at t is equal to 1 over sine of t. Can I multiply both sides by sine of t, get sine of t, cosecant t is equal to 1, and then solve for sine of t, give me 1 over cosecant t, right? Does that make sense to everybody? So those two things are both reciprocal identities. This one is what cosecant is in regards to sine. This one is what sine is in regards to cosecant. Okay. For the same reason, that one can be rewritten as cosine of t is equal to 1 over secant of t. That one there is tangent of t can be written as 1 over cotangent of t. And then the two on the right, those are just alternate versions of looking at tangent and cotangent as sine by cosine, and then it's reciprocal because sine. Those are things that might be useful later on. Okay. For instance, if we were to have maybe an expression at some point that said we have, cosecant squared t times sine of t. That's kind of ugly, right? That's an ugly expression. Okay. But if I know that sine of t can be rewritten as 1 over cosecant, does that allow me to make that substitution and get those to cancel, and all I'm left with now is cosecant of t? Does that make sense? Or even if it was just to the first power here, if I had cosecant t times sine of t. Now, my hopes are that those are reciprocals to begin with, and product of reciprocals is always 1. But if you didn't realize that right away, you can take the sine of t, rewrite it as 1 over cosecant of t. Now you do see it, they cancel, leaving you just 1. Does that make sense, everybody? So that's maybe a benefit, and I don't know how much you'll see that. You might see it 1 time throughout the whole course. You might see it 30 times. I don't know. Okay, but they are true identities that you might want to commit to memory. We talk about these Pythagorean identities. Remember, this is just a unit circle, right? Okay, and now that we know that our x value, so this is x squared plus y squared equals 1. X squared plus y squared equals 1. And we know now in the unit circle, every, this is x squared, because that's the cosine value. This is y squared, okay? But we know every point on the unit circle, the x value is equivalent to cosine. The y value is equivalent to the sine, right? Okay, so if we square those, accordingly, we should get 1. Then the remaining identities there, the remaining Pythagorean identities are just found by taking this thing here and dividing all 3 terms by sine squared. Okay, and that will actually give me this one over here. If I take this one here and divide everything by cosine squared, all 3 parts by cosine squared, and do substitutions, it will give me this one here. Okay. I'm not going to spend a whole lot of time on Pythagorean identities right now. We're going to devote a lot of time in chapter 7 to that. So even there's an example 6 here that we've kind of already done. I'm going to kind of skip over that just for the sake of time today. But we're going to do a lot of work in chapter 7 with identities and being able to work with those pretty fluidly. All right, so this question, we've already seen a variation of this question, so I'm going to show you how this chapter wants us to view it, and I'll show you how we've already viewed it in chapter 5, okay? Not the greatest at drawing circles. All right, so I got that circle. It's a unit circle, okay? So this point here is 1, 0. It says if cosine of t equals 3/5, and t is in quadrant 4. So t is somewhere in this on this arc and quadrant 4. So I'm just going to put it maybe right there, okay? So remember what that means to us. The t value is that arc, okay? And it provides this point, okay? And that point is a cosine, comma, a sine value, right? Does that make sense, everybody? What do they tell me that point's cosine value is in the question? 3/5. So the ordered pair here starts off as 3/5. Okay. Now you guys know, that because of the unit circle, we can write this a couple different ways. We can say either x squared plus y squared equals 1, or because we're in the unit circle and your x squared is, or your x is cosine, we can say that, and your y is sine, we could say that. Does that kind of make sense, everybody? So my cosine is 3/5. I put that in here and say 3/5 squared then, plus sine squared t is equal to 1. What is, so 3/5 squared is 9/25. Get that. What's sine squared t going to equal? 16/25. So then what's sine of t going to equal? 4/5. And the sine of t is the y value here, right? Now, just be careful because it tells me what quadrant. So what do I got to do with that 4/5? Make it negative. Okay. So once we have that information, obviously we know that that's the cosine. So that's cosine of t. That's sine of t. Can we figure out what tangent of t is? What's tangent of t? It's y over x, right? Or sine over cosine. So it's negative 4/5 divided by 3/5, so it gives me negative 4/3. What is the secant of t? 5/3. Secant's the reciprocal of your cosine, right? Cosine is 3/5. Reciprocal has got to be 5/3. What is cosecant of t? Negative 5/4. Is that all right with everyone? That is working in the unit circle, right? Okay. Let's kind of draw a comparison to what we've done in chapter 5. If we were in chapter 5, what we did when I said cosine of t is 3/5 and t is in quadrant 4, we kind of did this thing, didn't we? We drew out our angles. Okay, that angle, we didn't call it t, we probably called it theta, provides a terminal ray like that, right? And that terminal ray we then took and drew up from that terminal ray. That segment made it perpendicular. Okay, and now what we learned about that angle right there told us everything that we need to know about theta, right? Okay, well, when it says cosine is 3/5, doesn't that mean opposite, or sorry, adjacent is 3, hypotenuse is 5, and Pythagorean theorem tells me that this is negative 4. So here's the question. What is sine of that? Sine of that theta would be negative 4 over 5, right? It'd be that number right there. Tangent would be opposite over adjacent. It'd be negative 4/3. It'd be that one there, right? So what's the comparison here? What's going on? If we think about it, let me kind of clean things up here. What we did in, let me just open a new window. It's all messed up. What we did in chapter 5 was actually looking essentially at a triangle that was part of that circle, right? Where the radius was 5. So let me see here. Let's put in a point here. Let's put obviously our origin. So there's our terminal ray from chapter 5. And created give me a second. In chapter 5, we end up creating that right triangle. And what I can learn about that right triangle tells me then everything I need to know about the angle theta, right? Okay. Well, what we just did with chapter 6, what we did over here is working with that circle, okay? And now the triangle there, I'm not going to spend as much time as I did kind of creating the other triangle, but the triangle there would really be that blue one. Does that make sense to everybody? And what then do you know about that blue triangle, compared to the red one? They should be similar, right? Okay, by AA. Therefore, sides are proportional, so we're finding the exact same information out. Does that make sense to everybody? Okay, so I think I don't want you guys, and I teach it this way because of how I felt when I was in your seats when I was in high school. That facts were just given to me, they're just handed to me, and never really explained to me why they were what they were. Okay, and then it took me a long time. It was way beyond leaving high school. Okay, and I couldn't in high school. I couldn't tell you sine of negative t is equal to negative sine of t, and I can remember those facts. But I couldn't, if I forgot one, I couldn't on my own determine what they were or why they were what they were. Okay, I want you guys to be able to do that. I want you at some point to understand math and be able to teach somebody else the math, explain it to somebody else, explain maybe back to yourself, so that in the event you do forget it, you're able to still manipulate things and get to the answer that you need. I don't want you guys to be robotic. I'm more concerned, I guess, with the understanding of mathematics than being able to just recall facts, because that's not learning, right? Okay, repetition or memorization or repeating something, those are very, very low-level skills. But if you can understand the relationships and be able to synthesize and analyze something, that's when learning is taking place, and that's when you really know something. But I don't want you guys to have to sit in a calculus course at some point or a Calc 2 course at some point, and at the same time you're trying to learn that information, which calculus isn't hard, it's the algebra that you're probably going to have to focus on trying to relearn. I don't want you to have to learn the calculus, relearn the algebra, and then at the same time go back and say, okay, start from scratch, let's try to relearn the trigonometry that's being used inside this calculus question. Okay, so we're going to take time to kind of see those relationships and talk about them and see how they link. One thing I want you guys to understand that what a lot of mathematics does is shows you 2, 3, 4 different ways of doing the same thing, right? Trying to look from different perspectives. One perspective in chapter 5 was, okay, let's learn this information looking at a triangular relationship, okay? And view that from that perspective. This one is using a circle perspective, okay? But we're still gaining the same results, right? So as we move on throughout the rest of the course, we get into chapter 7, chapter 8, chapter 9. It's not going to force you to say, hey, use the triangle approach, or hey, use the unit circle approach. Most generally, a trig class is going to use the unit circle approach just because it's maybe a little bit more informative in regards to the recalling the sine, cosine, tangent values, but it doesn't ultimately really matter. Okay. What I want you guys to do real quick, draw a unit circle like this and give yourself some room, because there's going to be, I'm going to try to get you to replicate this thing on your own. Okay. Which would we all agree there's a lot of numbers up there? A lot of garbage. Okay. I'm going to try, so you're going to give yourself room so that you're not really cluttered and numbers right on top of numbers. You're going to see that when I do this, just so you guys can see things a little bit better, it does get kind of messy and get kind of cluttered. My thought is later this week to give you 2 circles, okay, and ask you to replicate what we're going to do kind of in a quiz format, okay. I think if you're able to do that, you're going to be able to, as we move through the course, recall, if I say what's the sine of 2 pi over 3, you automatically give me right of 3 over 2. Okay. And if I ask you what's the cosine of negative 5 pi over 4, you automatically give me negative right of 2 over 2. Okay. Because I think you guys have the capacity to do that. But it's much like learning vocabulary and learning, back to like geometry when you try to learn theorems and postulates and that kind of stuff. Don't you learn them a lot better if you write them out? Okay, instead of just seeing them. Writing something is, I think research shows, it's 6 times more effective than reading it. Okay, so if we can write this thing out 4, 5, 6, 7 times, it should make the rest of the course somewhat simpler. Okay, now here's the thing. What I want to do here is I just want to count. Okay? We're going to count from 0 to 2. 0 to 2. Now, why I'm counting from 0 to 2 is because this is 0 pi and 2 pi when I come all the way back around, right? So if you want to incorporate the pi's right now, you can. If you don't want to, that's fine. But if I'm counting to 2, right now my axes break up that 2 into how many slices, or how many parts? 4. So what I'm going to do is I'm going to say, okay, what is 1/4 of 2? And it gives me 1/2, right? So what I'm going to do is I'm going to go through 0, and I'm going to add 1/2 to that. And then from 1/2, I'm going to add 1/2 to that. And then from 1, I'm going to add 1/2 to that. Writing these all as fractions, obviously. And then from 1.5 or 3/2, add 1/2 to that, don't I get to 2? And now go back and put pi on those things. And those are our quadrantal measurements, or angles, if you want to think about it that way, for those locations, right? Does the line y equal x cut the first and third quadrant directly in half? That line right there, cut that in half. Okay. Does the line y equals negative x cut those 2 in half? So now how many total slices would you have here? 8. Okay, so with the axes in those 2 lines, y equals x and y equals negative x, we get 8 total slices. So what I'm going to do is I'm going to take 1/8 of 2, and that gives me 1/4, right? So now I'm going to go around, I'm going to count by fourths. Start at 0 again. This point here now is 1/4. Add a 4th to that, and I get right here, right? I get back up to 1/2. And I've already got something written there, so I don't need to write, I don't need to write that that's 2/4. I could if I want to, but you don't need to. Does that make sense? Okay. Go here, add a 4th, I get 3/4. Add a 4th, and I get 4/4, right? Add a 4th, I get 5/4. Add a 4th, I get there, correct? Add a fourth. I get to, so this would have been 6/4, right? Is everybody okay with that? What's a fourth plus 6/4? 7/4. And then I get to 8/4, right? Which is just 2. Go through and throw pi on those. So now we've got our Porter marks, right? Well, to get this one here, because we're kind of associated, I'm going to do it in degrees, or think about it in degrees. We're 30 degrees there, right? Would there be one here of another 30 degrees? And then another 30 degrees would get me to 90? How many of those slices would I have all the way around? 12. So what's a 12th of 2? 1/6. So let's go through and count by 6s. 1/6. Okay. Jump over here to this point would give me 2/6. Now doesn't this one give me 3/6? Which 3/6 is the same thing as 1/2, right? What's 3/6 plus a 6? 4/6. 4/6 plus a 6 is 5/6. 5/6 plus a 6 is 6/6. Then I'm going to have 7/6. You guys see how we're just basically counting by 1 here? 6, 7. This one's going to be 8. This one's going to be 9. And we're going to have 10. And then we're going to have 11. And then we're going to have 12. Does that make sense to everybody? And if you think about, I just started counting by 1s there, but if we did the same thing with pi or 4, we did 1/4, 2/4, 3/4, right? That's what with the denominator 4. The numerals go 1, 2, 3, 4, 5, 6, 7, 8 all around. With the denominators of 6, we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way around. And now we're going to go back through, and we're going to put pi on all of these. And each one that needs reduced, we're going to reduce it. Okay? So this is pi over 6, right? 2 pi over 6. What's 2 pi over 6 the same as? Pi over 3, so that's where that shows up or comes from. We get pi over 2. 4 pi over 6 would be 2 pi over 3. 3 pi over 4, 5 pi over 6, that's 1 pi. 7 pi over 6, 5 pi over 4. 8 pi over 6 is going to be 4 pi over 3. Got 3 pi over 2. 10 pi over 6 is going to be 5 pi over 3. And then 2 pi. Okay. Again, why do I teach you this? When I was in high school, that was printed out, given to me, and said memorize it. No, don't do that. That's stupid. Okay. There's a lot of numbers there, right? A lot of them are the same, right? Except for signs and position, that kind of stuff. If you try to memorize that, you are going to mess something up. Okay? But if you can count by 4s and 6s, okay, all the way up to 2, you should be good. Okay? And really what we probably should have done, guys, is we probably should have started with counting by, 1/12 of 2. We should have started counting by 1/6 because that would knock that one off, that one off, that one off. It would give me all of them except for the 4ths, right? Either way, it doesn't matter. But now, we know we got to find some ordered pairs here. Try to give you a technique for remembering ordered pairs. The only numbers that are going to show up, other than 0 and 1, are 1/2, radical 2 over 2, and radical 3 over 2, right? As decimals, that's 0.5, that's 0.707, that's 0.866. So we know which one's smallest and we know which one's biggest, right? Think about these 3 points right here in the first quadrant. I've got to travel to pi over 6, I've got to travel that purple distance. To pi over 4, I got to travel that green distance. And then to pi over 3, I got to travel that red distance. Does it make sense which one of those is largest? The purple one, right? So does it make sense that's got to be radical 3 over 2? That's going to be radical 2 over 2. And that's got to be 1/2. Does that make sense to everybody? All right. I will finish. All right, so the class ended a little bit ago. I'm not sure where I was, but just kind of start over from the explanation that I know everybody at least heard in class. Once we have the unit circle created with the measurements of in terms of radians, we then want to put it in the ordered pairs. So understanding that other than, obviously we got 1, 0, and 0, 1, and then -1, 0, and 0, -1 for those quadrantal angles. But what ends up being the only numbers that get used for the rest of the circle are 1/2, radical 2 over 2, and radical 3 over 2. And if you ever forget where they go, you could either use special right triangle, which is essentially what I'm looking at here, just individual parts of it. But if I put these numbers in order, 1/2 is 0.5, radical 2 over 2 is 0.707, radical 3 over 2 is 0.866. And then I think about, remembering we're in the coordinate plane. So there is a grid here, and we're traveling an x distance and a y distance to get to these locations, to get to these points. Understanding that if I wanted to get to pi over 6's point right here, then I need to travel a longer distance horizontally than I would if I wanted to go to pi over 4 or if I wanted to go pi over 3. So looking at these numbers, the only numbers that get used, the longest one is 0.866, or radical 3 over 2. So that's why this x value is radical 3 over 2. That distance, that x distance, is longer. This distance here is in the middle of the x distance that would be required to get to pi over 3 or pi over 6. Pi over 4 is in the middle. So I come over here and I find the middle value. It's radical 2 over 2, and that's that x value. And then the red one is shortest. So going from 0, 0 to pi over 3, I would travel the shortest horizontal distance. So that's why that's 1/2. Now the same thing can happen when we talk about vertical distances. Okay, if I wanted it, once I got to the spot on the x-axis in which I can transition and start moving vertically, I'm going to have 3 different vertical values. I'm going to have this distance here. I'm going to have that distance there. And I'm going to have that distance there. So now we see that the blue one is bigger. So the blue one is going to be root 3 over 2 right there. The red one is the middle one, so that's root 2 over 2. And the purple one then is the smallest one, which is going to be 1/2. And now that you have those, it's just a matter of folding on the y-axis, and this point is going to go right there. This point is going to go right there, and that point is going to go right there. But then the only thing you would change, the coordinates are going to be the same, but the only thing you would change is all the x values become negative. And once you have those, then that point right there is going to go there, that one there, and that one there. The only thing there then is that all the x's are negative and all the y's are negative. But as you fold on the x, that point should have gone there. Because of symmetry, that one goes there. And again, because of symmetry, that one goes there. And now all of those points are the same coordinates, except for now the x's are positive and the y's are negative. Remember, every point in the first quadrant is that. Every point in the second quadrant is that. Third quadrant is that. Fourth quadrant is that. So if you remember that, that's going to help you generate the unit circle if you ever get stuck. And we will have a quiz over this in the near future, so please, 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 please take the time to learn that.